Hello, everyone, and thank you for watching. And I would love to help you understand um, kinetic energy, potential energy, total energy, and total energy in this case, the sum of kinetic energy and potential energy will be mechanical energy. And so I'll be showing several instances of what that looks like. So have a look at this simulation I have here of a ideal pendulum. An ideal pendulum has a mass at the end of a very thin string. We will ignore the effects of the mass of the string, and we'll pull back the pendulum. It turns out a little bit less than 15 degrees or so, and we're going to assume there is absolutely zero friction or air resistance or energy loss to any dissipative or non-conservative force. And with that, what we should see is we should see that the energy varies in time in terms of the potential energy and the kinetic energy, but the total energy, which will be the sum of the kinetic and the potential energy, which will be the mechanical energy, should stay constant with time. That is to say, the only force that is doing work is the gravity force, and it is a conservative force. So we can write a potential energy function from that, and we should conserve this quantity of mechanical energy. So let's have a look at what this looks like. Let's pull the pendulum back several degrees, and let us do start in just a moment. But when we do start, I think we should start with all potential energy. The initial speed should be zero, so the kinetic energy is zero. But if we define the lowest height of the pendulum as h equals zero, that is zero height for gravitational potential energy, then the potential energy should be zero when the pendulum swings through the equilibrium position. And the kinetic energy should be maximum because when we've reached the bottom of the swing, equilibrium, when the pendulum momentarily is straight up and down, the speed is greatest and the kinetic energy is also largest. Then another quarter period later, or a quarter of the swing, oscillation, then we should be back to maximum potential energy and zero kinetic. And this should go on as waves that oscillate in time, such that we continually go from max to min to max to min of the potential and the kinetic energy, and they're exactly 180 degrees, or you might say pi radians, out of phase if you started to think about this in radians. But this, in terms of time, they should be exactly half a period out of phase. So let's go ahead and start this. So we do see that the potential energy starts at a maximum value. If I pause it right there, when the potential energy is back to its maximum value, the kinetic energy is zero. When the pendulum is swinging through the equilibrium position, the kinetic energy is maximum, the potential energy is zero. But notice the sum of the potential energy and the kinetic energy is always a constant. That is to say, the mechanical energy is conserved. This time we'll be taking a closer look at the pendulum, but we won't be plotting the energy as a function of time on a two-dimensional axis. We'll actually be plotting two things. We'll be plotting the potential energy as a function of x, and x is the position going to be either left or right from straight up and down, that is the origin. And as x varies, you'll see that the potential energy will vary, but also you'll see over time the start will be all potential energy, and the total energy, which is the mechanical energy in the absence of air resistance, will then become all kinetic energy at the bottom, and then we'll be back to all potential energy at the top. Now, by the way, there's a couple things we can say about this. So let's start. So notice that this is conservation of mechanical energy in the absence of air resistance. Notice that anywhere we go on this graph, the slope, that is the negative slope of the potential energy versus x, is going to be the gravitational force, because the slope of the potential energy versus x graph, horizontal spatial derivative of potential energy with respect to x with a minus sign, is going to be the force of gravity takes the pendulum bob down gradient. That is to say, we know that balls go downhill and a pendulum swings down towards its lowest potential energy. But then the kinetic energy, by inertia, takes it back up to its potential energy again. Notice that right here at the bottom of the pendulum bob swing, the horizontal derivative is exactly 0, and that's because there's no change in the potential energy at the bottom. So in fact, exactly at the bottom, gravity does 0 work, and that's because the gravity force is straight down, the displacement is straight to the right, or if it's going the other way, straight to the left, and the cosine of the angle between those two vectors is the cosine of 90 degrees, which we know to be exactly 0. So since gravity does 0 work at the bottom of the pendulum swing, gravity doesn't change its potential energy at that point. It's only the kinetic energy that, via inertia, continues the pendulum on its swing. Okay. Now, what if the initial angle was larger? Well, you'd imagine that we put more potential energy into the system. That is to say, if we put more potential energy into the system, there should be more total energy. What do you think should happen to the speed of the pendulum bob at the bottom? So pause, talk to your neighbor, talk to your dog, talk to your cat, and see what you come up with. Okay, so hopefully you came up with the fact that the speed should be greater and the kinetic energy should be the exact same size as the total energy or potential energy here. So the pendulum bob should be indeed moving faster. And that is exactly what we observe. We observe that the bar graph has the bars of potential energy and kinetic energy varying with time. The total energy is time invariant. It stays constant with time. But at any moment, the sum of the kinetic energy and the potential energy equals the total energy. Okay. And this is what we mean by a potential energy versus position graph. We'll use this many times in a calculus-based physics class. And here I have another example of conservation of mechanical energy. In this case, we will throw a ball straight up into the air. In the absence of air resistance and any friction dissipating forces, all the forces are conservative because it's only going to be the gravitational force, and we'll again have conservation of mechanical energy. At first, when the person throws the ball, the kinetic energy will be maximum. When the ball gets to its maximum height, the gravitational potential energy will be maximum, but the kinetic energy should be 0, and when the ball falls back down, even though the velocity will be negative, the ball will be going down. When you square a velocity that's negative, it's positive in the 1/2 mv squared, that is the kinetic energy equation, so you'd expect the kinetic energy to be back at its maximum when the ball reaches the person's hand once again. Now, with that in mind, we would expect that the velocity versus time graph should look like what we learned in kinematics. Start off at its maximum positive value, go to 0 when the ball is at its maximum height, the top of its trajectory, and then when we get back down to the hand, it should be the same speed but opposite direction, so a negative velocity, as it's about to reach the hand again. The height versus time graph should look like a downward facing parabola because it has negative concavity. That is, the acceleration is negative 9.8 meters per second squared all the time, constant here on Earth in the absence of air resistance. And This is what we'd expect. So potential energy is just going to be the constants mg times that h. So it should have the exact same shape, but a different scale because it's the potential energy. The kinetic energy should be exactly the opposite as a function of time for the tossed ball. But the total energy should remain constant because this is conservation of mechanical energy. So let us throw the ball and let's observe what we see. Indeed, we do see that the velocity starts off positive, goes to 0 at the top of the trajectory, becomes negative. The downward facing parabola is the height versus time graph of this ball. The potential energy graph matches that, just with slightly different units. The total energy remains constant. That's because the kinetic energy is exactly the complement, you might say, of the potential energy. When the potential energy is 0, the kinetic energy is max. There's a point where the two of them are equal, but then the kinetic energy is 0, the potential energy is maximum, and everywhere as a half sinusoidal wave sort of in between. So watch one more time. For a throw, this is what we mean by the conservation of mechanical energy. Okay, that's exactly what we just described. So I hope that really makes sense. The last two examples I want to look at here include a spring with a mass on a frictionless horizontal surface. Now a spring with a mass that's on a horizontal frictionless surface should also have conservative forces because we can define a potential energy from the Hooke's law spring force. The Hooke's law spring force, like any conservative force, does not depend upon the initial and final positions. It depends upon the initial and final positions only. It does not depend upon the path that the object takes to get there. So notice, when we take the mass and we compress the spring, we should have all potential energy only. But the potential energy is elastic potential energy, namely that 1/2 kx squared we see there. Notice that the potential energy is all the total energy, and the force is exactly in the opposite direction from the spring as the applied force by the hand. When we let the mass go, all the potential energy becomes kinetic energy. So we transfer potential energy to kinetic energy by doing work. The spring force is to the right, the displacement is to the right, the spring does positive work on the mass to cause the mass to accelerate and gain kinetic energy. Now, what if we were to compress the spring further? Well, if we compress the spring twice as much, I think we should have twice as much potential, not twice as much, but there's an x squared there. So we should have 4 times as much potential energy. So we should probably have twice as much velocity as we had in the first case, and we should certainly have more kinetic energy. The mass should be moving faster. And indeed, that is what we observe. So, greater compression of a spring, greater elastic potential energy buildup, greater work done by that spring to release the mass, and thus also greater kinetic energy that results. Finally, here is one more case of the conservation of mechanical energy, namely for an oscillating block spring system, again on a horizontal frictionless table, absence of air resistance or any non-conservative dissipating forces. So notice what we have here is a spring which we can compress. When we compress it, we're going to have only elastic potential energy. When we release it, it should have kinetic energy, but the potential energy will become kinetic energy when it moves through the equilibrium position at x equals 0. The kinetic energy should be maximum. Why? Because the spring has done work on the mass to cause it to accelerate and gain kinetic energy. Now, via inertia, when the mass overshoots the equilibrium position, we start to elongate the spring, and that stores elastic potential energy again. It should be the exact same amount, but the spring will be elongated, not compressed. And the process should continue, the spring having its maximum, the mass having its maximum speed and maximum kinetic energy through the equilibrium position, and the spring having its maximum potential energy when fully compressed or fully elongated. And because the equation is 1/2 kx squared for the elastic potential energy, it won't matter if it's fully elongated or compressed. That'll be a positive potential energy. And it won't matter if the mass is moving left or right. The velocity is squared, and so as a result, we should have a positive potential energy. So let's release it. Notice that one more thing, the force is always in the opposite direction of the x value. If x is negative when it's compressed here, the force is positive. You'll notice that when the spring is fully elongated, when x is positive, the force is negative, because the Hooke's law of spring force always tries to bring the mass back towards equilibrium position. It is a restoring force, trying to restore it back towards equilibrium. But we should observe this oscillation. Okay, and this is what we observe. So notice that when the block is fully compressed, the force is to the right. That's because the x value is to the left. Okay, notice that the velocity is 0 when the object is fully elongated or fully compressed, but when it's moving through equilibrium position, that is x equals 0, the speed is maximum. Notice the total energy remains entirely constant. That's because the potential energy is maximum at full elongation or compression, whereas the potential energy is changed into kinetic energy as the object moves, and the kinetic energy is maximum as it moves through the equilibrium position. If we reset this and we increase the Hooke's law spring force, what do you expect should happen to this energy graph, and what should happen to the plot of elastic potential energy versus position? That is the energy graph, the potential energy graph. So talk to your cat, talk to your dog, talk to your neighbor, maybe take a pause and then come back. Okay, so welcome back. Hopefully what you said is you said that the slope of the parabola should be steeper. Why is that? Well, we know that the negative spatial derivative of the potential energy versus position, that is minus dus dx as a derivative, is going to be the Hooke's law spring force. And if the spring constant is greater, you can imagine that's a more tightly wound, tighter spring. So if the Hooke's law spring force is greater, there should be a greater potential energy built up, more energy built up, and thus you'd expect a steeper potential energy versus x curve, and then also greater forces and greater kinetic energy, and thus larger speeds when the thing is moving. So let's increase the Hooke's law spring force by increasing the spring constant, and indeed we do have greater slope to the potential energy versus position graph. Let us compress this spring to that 80% we had before, and look at this. Now we have a much larger spring force ready to go, and indeed we do have greater restoring force, that is greater Hooke's law spring force, which results in a greater amount of potential energy stored in the spring, thus also a greater kinetic energy and a faster speed, and this is what we would expect to observe. Remember, this is conservation of mechanical energy in a system in the absence of dissipating forces. This concludes the conceptual intuition tutorial about energy and conservation of energy, mechanical energy, potential energy, and kinetic energy. and also energy graphs, that is potential energy versus position and their derivatives to get forces. Thank you very much for your attention. I will see you in the next video.